Bam! Mr. Tarrou. In this video, we're going to be taking a look at two ways of solving where two lines intersect in three-dimensional space. I'll put timestamps to the examples if you want to jump ahead. In the description, you'll also find a link to a playlist that includes all my videos that involve vectors somehow. And for our first example, which we're going to work twice, we're going to find, if possible, the coordinates of the point of intersection of the pair of lines. We have both of these given to us in Cartesian format. The first way we're going to do this is exactly how we solved the intersection between a line and a plane. We're going to take one of our equations, I'm going to work with the yellow one, come up with this, break this up into three parametric equations where not necessarily going to look at some known point on this line, but we can see maybe this white equation is given this particular line, and then this yellow equation in parametric form, we could identify a known point, but from that known point we have a directional vector, maybe we call it vector u, with some kind of scalar multiple on it. Well, we can just find, since this will be x, y, and z, each of them in terms of, we'll do lambda, we're going to take those expressions, plug them into this equation, and find out what that lambda has to be so that we get this yellow line, a point that satisfies the equation of this yellow line, but also satisfies the equation of this white line. And then when we find that lambda, we can take that value of lambda and plug it back into those parametric forms and find the point of intersection. Again, this is exactly how we found the intersection between a point and a plane. I'll have a link to that video in the description as well. The second way we can look at this is as a system of equations, like when we did linear combination in Algebra 2, where we look at the equation, this one part with x and y, in the yellow equation, this part with the x and y, and solve for x and y. And then use that in the second part with the y variable and the z, and make sure that we're getting the same value of z from both of these equations. And if we do, then this solution has one unique, this problem has one unique solution, and we will have found it. So here we go. We're going to say that in yellow, x minus 5 over 2 is equal to lambda. That's going to give us x is equal to 2 lambda plus 5. Looking at our second part here, we have y minus 7 over 2 is equal to lambda. That's going to yield y is equal to 2 lambda plus 7. And then our last part of this Cartesian form for a three-dimensional line is, or line in 3D space, negative z minus 4 is equal to lambda. Negative z is equal to lambda plus 4. Z is equal to negative 4 minus lambda. Great. Now, we need to find lambda such that it satisfies all three parts of this equation in white. And you can't work with all three parts of an equation at the same time. We're going to basically be looking at two separate equations. One built off the variables of x and y, find out what lambda is, and another equation built off the variable of y and z, and find out the lambda that's a solution to that equation. And we do need the same value of lambda both times. If we get lambda equals 2 and lambda equals 1, well then we're looking at an inconsistent system and there is no solution. So, and I need a piece of chalk here that's not broken. Ah, yes. Here we go. So we have x, which is 2 lambda plus 5, minus 1 is equal to 3 minus our expression for y, which is going to be 2 lambda plus 7. Kind of basically doing like a substitution process here for solving a system. Now we have, for our second equation, 3 minus y, which again is going to be 3 minus 2 lambda plus 7 over 3 is equal to z, which we have up there in terms of lambda from the yellow equation, negative 4 minus lambda plus 2 over 4. Okay, and to make this work a little bit easier, I'm going to multiply both sides of this equation by 3. And actually probably want to write it like this. But we're looking at 6 lambda from 3 times 2. We have 5 minus 1, which is 4, times 3 is 12. Now here, the multiplication and division of 3, of course, cancel out. We're going to distribute this negative 1, and we're going to have 3 minus 2 lambda minus 7. So we're going to bring this negative 2 over to the left by addition, so that's going to give us an 8 lambda. We have 3 minus 7 is negative 4. Negative 4 minus 12, to bring that over with subtraction, of course, is going to give us negative 16, and lambda is equal to negative 2. If I get the same value of lambda in this equation, we're good to go. There's a solution. We can plug that into these parametric equations and find our point of intersection. This time we're going to multiply both sides of the equation, and for room, I'm just going to write this once, 12. So 12 divided by 3 is 4. 4 times 3 is 12. I'll just leave that multiplication of 4 in front of this parentheses. So 12 minus 4 parentheses 2, lambda plus 7. And over here, the 12 divided by 4, is equal to 3. So we're looking at, well, I can do this. 3 times negative 1 is negative 3 lambda. We have negative 4 plus 2, negative 2. Negative 2 times 3 is negative 6. Okay, now watch me have some kind of small mistake because I'm doing so much in my head. But we're going to distribute this negative 4. We have 12 minus 8 lambda minus 28. Yes, equals negative 3 lambda minus 6. We're going to bring this negative 8 lambda over to the other side with addition, so we get a positive answer, giving us 5 lambda. Now we're looking at, let's see here, we're looking at 12 minus 28, which is going to give us negative 16, and negative 16 plus 6 is going to give us negative, oh, I can't believe I just said that. It's going to give us negative 2, negative 10. I'm jumping myself to the answer. So we have 12 minus 28 is negative 16. Negative 16 plus 6 is going to give us negative 10. Divide by 5, and we get lambda again is equal to negative 2, which is good. We have the same answer for lambda from both of these equations. Once again, that means there's a unique solution. We're going to find it if this was 1 and negative 2, or if they just weren't the same. Inconsistent, no solution. These lines do not intersect. They're either parallel or skew. And actually, if you write both of these in parametric form, you can get that, that directional vector and see that, if they're scalar multiples of each other, parallel or not parallel. So we have got x equals 2 times negative 2 plus 5. So we're looking at x is equal to negative 4 plus 5 is 1, not negative 1. And we're going to take that negative 2 and plug it up into here for y. We have y is equal to 2 times negative 2 plus 7. So we're looking at y is equal to negative 4 plus 7, which is 3. And finally, we've got z is equal to negative 4 minus negative 2. Z is equal to negative 4 plus 2, which is negative 2. The point of intersection is 1, 3, negative 2. And I made this example, not pulling them out of the book, and you might see that up here we can potentially, hopefully see, if you get the coefficients of x, y, and z to be equal to 1, that we are looking at, you can find that coordinate within this equation, but that's just because I made this, made this up and I wanted it to come out cleanly. This point is actually in this equation. So if you were to take this first y equation and write it in parametric form, and take those expressions of x, y, and z that are all in terms of lambda, and plug those parametric equations into this yellow one, you'll find out that lambda comes out to be 0. So when you work out finding the intersection of two lines in three-dimensional space and you want to work through the parametric form, how you work out your problem will determine what your value of lambda is, because here it could have been -2 or 0. So if you're working with somebody in your class and you get different answers for lambda, don't just automatically assume that one of you has made a mistake. If you want to make sure this is the right answer, just take your values of 1, 3, and -2, plug it in here, and make sure that you're getting a true statement, that you're not getting some kind of false statement like, well, let's see here, 1 minus 1 is 0. We've got 3 minus 3 is 0, and we've got -2 plus 2 is 0. So the true statement is that 0 equals 0 equals 0. If I were to plug these x and y, z coordinates into here and get something like 0 equals 5 equals 0, well then you've made an error somewhere, because we found this point from one equation. Let's find out, were those values of lambda actually consistent? Now let's look at this problem another way right now. Same equations, same problem, different method. If you don't want to go into parametric form, another way of doing this is basically going through like a linear combination process that you did all the way back in Algebra 1. Again, you can't look at all three parts at the same time, but you can write, well, x minus 1 is equal to 3 minus y over 3. Multiplying both sides by 3, we get that 3x minus 3 is equal to 3 minus y, and that's going to give me 3x, adding both sides by y and adding by 3, 3x plus y is equal to 6. If I do that same process and write an equation in terms of x and y with these first two parts of my Cartesian form of this line, we get x minus 5 over 2 is equal to y minus 7 over 2. Now this is going to come out really nice. Multiply both sides by 2, and my division cancels out completely, and we're just looking at x minus 5 is equal to y minus 7, or x minus 7, subtracting this, okay, let's try that again. Subtract over the y, add over the 5, and we get x minus y is equal to -2. And I got a little 2 by 2 system here. So we've got 3x plus, actually let's go ahead and write this up here. So 3x plus y is equal to 6, and x minus y is equal to -2. Well, this is already set up to just do linear combination. You already have opposite coefficients on y. Just add those up. We get 4x is equal to, well, 4 divided by 4, and x is equal to 1, which that's going a little bit quicker than it did actually in the first process where we found that scalar multiple in the directional vector, going through the parametric form. Now we're going to say, well, if x equals 1, we have 1 minus y is equal to -2, negative y is equal to -3, and y is equal to 3. So we actually already have 2 of our 3 parts of this coordinate. For finding out what z is equal to, don't get lazy. You can't just look at, let's say, one of the equations, and here's what we're going to do. We're going to look at 3 minus y over 3 is equal to z plus 2 over 4. We're not going to take this value of y and plug it in here and solve for z. We are, but that's not all we can do. We have to take this value of y and plug it into both of these equations and make sure we get the same value of z. I think that's the main disadvantage, or where the most students are going to get in trouble with solving for where two lines intersect, at least through this just pure algebraic process and not finding some kind of scalar multiple of the directional vector, is going to just one of the equations, finding that third part of the coordinate and thinking that you're done. You're not. So we're looking at, I'm looking like I'm going to run out of room. 3 minus 3 over 3 is equal to z plus 2 over 4. Well, this is going to give us 0. So we have 0 equals z plus 2 over 4. Multiply both sides by 4. That's going to give us 0 again. and negative 2 is equal to z. Will we get that same negative 2 when we plug into this equation here? So we're looking at y. Maybe I should do it in yellow since it matches that one. Y minus, well, y is 3. 3 minus 7 over 2, so 3 minus 7 over 2 equal to negative z minus 4. That's going to be negative 4 divided by 2, which is negative 2. Add 4 to both sides, we get 2 is equal to negative z, and we see that z is again equal to negative 2, just like it was here. And it also worked out in the first way that we worked out our problem. So one more time, our point of intersection is 1, 3, and negative 2. So now you know how to find the intersection of two equations, two lines that are in three-dimensional space. I have one more example coming up. It's going to be a lot shorter because actually it's not going to have a solution. No. It's our last example. All right. Now, we have the equation of a line given to us in vector form, but not vector form in terms of vectors given to us in column component form, but basically a sum of component vectors. And what you want to look at here is we're just basically looking at movements along the x-axis, movements along the y-axis, and movements along the j-axis. And we can pull out of here that our known point, or basically if you think about vector r is equal to vector a plus lambda times vector u, that the position vector for our known point is equal to negative 2, 1, and negative 1. And our directional vector that has that scalar multiple of lambda on it is, well, the coefficients of lambda. So our directional vector is 3, 1, and negative 1. Has the directions of is 3, 1, and negative 1. Okay. That being said, we can look at this and see that in parametric form, x is going to be equal to negative 2 plus 3 lambda. Y is equal to 1 plus lambda. And z is equal to negative 1 minus lambda. You can also just basically see that right here in our equation. So now that the first equation basically really is set up for us to work through the parametric forms. It'd be more work to put this into our Cartesian format and then do that systems of equations basically. We're going to take the expressions of x, y, and z just like before, plug it into the first two parts to make our first equation. 2 times x, 2 times negative 2 plus 3 lambda is equal to y, which is 1 plus lambda. And our second equation, which is going to be made up of our second and third part of our Cartesian form of this line in 3D space, y one more time is 1 plus lambda. Z, which we have negative 1 minus lambda, plus 1. And just solve for lambda. Find it, plug it back into these three equations that are in parametric form, and you got your intersection point. Unless, of course, it comes out to be inconsistent. So we have 2 times negative 2 is negative 4. 2 times 3 is 6. 2 times 3 is 6 lambda. Try that again. Equals 1 plus lambda. We're going to subtract both sides by lambda. Get a 5 lambda. Add by 4. And get 5 lambda equals 5, and divide by 5, and lambda is equal to 1. So far, so good. Except, over here, we're going to add by lambda and get 2 lambda. We have negative 1 plus 1, which is 0. Now we're going to subtract 1, so we have 2 lambda is equal to negative 1, and lambda is equal to negative 1/2. Well, first two parts gave us 1, second two parts gave us negative 1/2. Conclusion, 1 does not equal negative 1/2, Therefore, there is no solution, i.e., the lines do not intersect. I Mr. True. Bam! Go to your homework.